All right, so now let's summarize what we've learned so far. We've learned 4 different shapes: uniform, skewed to the right or to the left, bimodal, and normal. We've also learned asymmetric and symmetric. So here I'm asking, is this one symmetric or is this one asymmetric? Well, the uniform one, yes, it's largely symmetric because rectangles are symmetric. Skewed, are they symmetric? No, because either the right tail is long or the left tail is long. Bimodal, are they symmetric? This one's sort of a sometimes. There can be times when these are symmetric. For instance, if you have 2 that look like that, it's roughly symmetric. But you may also have bimodal distributions that look like this, right? And then that one doesn't look as symmetric, right? Normal distributions, yes, they are symmetric, always. And I'll just draw these here, just so that you know. All right, so now let's talk about the centers. Does it have a clear mode? Well, here it doesn't really have a mode. There's not one most frequent value. In fact, all the values are roughly similarly frequent. So we'll say no, it does not have a clear mode. Typically, the skewed distributions are unimodal. So yes, unimodal. What about bimodal distributions? Do they have a mode? Yes, they are overflowing with modes. They have 2 modes, in fact. Sometimes more. You could have trimodal, right? So yes. What about normal distributions? Well, of course, it has a mode because it's also unimodal. All right. Now let's talk about spread. What does spread look like here? Well, the spread is roughly even, and it goes as far as the values go, right? Does it use the point of inflection? No. What about in a skewed distribution? Do we use point of inflection there? Well, in a skewed distribution, the point of inflection is weird because the point of inflection is going to cut it up at different places depending on whether you look at the right side of the mode or the left side of the mode. So point of inflection isn't quite as useful here. In a bimodal distribution, sometimes you could use the point of inflection, but it gets complicated. So we'll write in, it's complicated. Really, it's only for the normal distribution that the point of inflection comes in really handy. It's a resounding yes. And at the distance from the mode, or the center, to that point of inflection, distance is called the standard deviation. All right. Now let's go on to some examples that you might frequently see in textbooks, AP statistics, as well as a lot of general reasoning sorts of questions. These are what I like to call sketch problems. They give you some sort of data set that you probably only know a little bit about, and they ask you, what kind of distribution do you think it might have? We can answer these questions now. So here's sketch problem number 1. What if you were asked to imagine the age of each person who got his or her first driver's license in your state last year? Now, that's going to be a distribution. It's a whole bunch of numbers, right? A whole bunch of different ages. So let's think about this. On the x-axis, we'll probably put age. Now, here we're going to put frequency, but I'm not going to draw that in just so frequency. Actually, I'll draw it in. Here's the y-axis. All right. So now let's think about this. Is there some sort of minimum or maximum age at which you could get your driver's license? Why, yes. Probably 16 in most states, right? So we'll put 16 as the minimum age. And probably a lot of people get their driver's license sort of early on, so from like 16 to age 20. But there are probably very few people getting their first driver's license ever by the time they're 25 or 30 or 40, even fewer people, right? So that's already starting to sound like maybe somewhat of a skewed distribution. Probably lots of people in their early sort of 20s, maybe late teens, getting their driver's license, and very, very few outliers who are getting their first driver's license when they're 40 or 50, right? Maybe that's 40, right? So even though you might not know very much about people getting their first driver's license, you can already tell the shape of this distribution. It's skewed, but not only skewed, but the tail is to the right, so we call that skewed right. It's probably unimodal, or there's probably some cluster up here, and it's probably asymmetric because it's skewed. All right, next example. So here's sketch problem number 2. Let's think about the life expectancy of females in Africa and Europe. So when we think about life expectancy, that's considering how long are females in Africa and Europe going to live. And so age, or years, should probably be on the x-axis. On the y-axis, once again, we're going to be looking at frequency. I'll just say freq. Now, let's consider the life expectancy in Africa and Europe. Now, Africa has a lot of diseases and malnutrition and other factors that are going to affect life expectancy of females. Also, Europe, on the other side of the spectrum, is going to have a lot fewer of those same issues. So the life expectancy of males in Africa might be shorter than the life expectancy of those in Europe. So we might see something like a bimodal distribution that's actually caused by 2 unimodal distributions. So let's put Africa, let's say, in red, and European females maybe in blue, right? And so maybe most European females die, I don't know, when they're older, like 70. But maybe in Africa, the life expectancy is less, so maybe 50. So here we see 2 unimodal distributions. But it didn't ask us to plot these separately. When we combine these, we see a bimodal distribution. All right, let's go on to the next problem. All right, sketch problem number 3 says, well, what about the distribution of the last 2 digits of the telephone numbers in the town or city where you live? Do we have any reason to believe that those 2 digits are going to be, some digits are going to be more favored than others? Well, let's think. The last 2 digits of the telephone numbers. If we put that on the x-axis, basically we could go from 00, oops, pen followed me over. We could go from 00 all the way up to 99, right? That's our sort of range of possibility. And let's see, what might the frequency be? Well, we don't really have a reason to believe that 00 is more or less popular than 99. And we don't really have a reason to think 99 is more or less popular than 62 or 47 or 35, right? So we might be thinking about a roughly unimodal distribution, where each of these are roughly equivalently popular, right? So you could continue that on. So this is probably one of those unimodal distributions where the numbers don't pile, one of the numbers is way more frequent than another one. Now let's move on to sketch problem number 4. What about the length of time students use to complete a final exam within a 50-minute class period? Well, let's put minutes on our x-axis, minutes, and the frequency over here on the y-axis. Now, since it's a 50-minute limit, 50 is going to be the max value. People shouldn't be allowed to use 51 or 52 minutes. So the numbers will probably bunch up against that wall. Remember, skewed distributions usually happen when there's some sort of wall, imaginary wall in this case. So probably most students might take maybe a little less time, a little more time, maybe somewhere close to 50, and maybe some students will take all the way up to 50 minutes. So maybe the students will be clustered around there, and probably very, very few students will finish it in like 10 minutes or 20 minutes, right? So maybe it'll look something like this, right? So fewer students are finishing it in 10 minutes, but maybe there's one really fast guy who does. Maybe just a few more finishing it in 20 minutes, but most of the students finishing around 40 or 50 minutes.